and welcome to the SeaBioComp event here at the CETI Park and also online. I'm Jeanne Mélier. I'm in charge of innovation at the EuraMaterials cluster, which is hosting the SeaBioComp event here. We will have a first set of presentation on the results of the SeaBioComp project with Centexbel, ARMINES and CETI on the different experiments for the development of biobased composites. Then we have a break of 20 minutes, about 3 p.m. And then after the break, we have the other presentation of SeaBioComp project from the University of Plymouth, IFREMER, and we finish with presentation from KU Leuven and Green Boat with example of application and prospects for composite based on natural fibers. We propose you to ask your question at the end of each set of presentation, and for those who are online, you ask your question on the chat. So EuraMaterials is both here a place that hosts an incubator, startups and companies involved in materials, and our cluster is the competitiveness cluster for the material processing industries and concern all materials, textile, plastics, paper, cardboard, glass, ceramic, wood. And our mission are to support companies in their innovation project for their in seeking partners or funding or where to build their project. So EuraMaterials also offers events that you can consult in the agenda, and not our technological days in a few days in May 19th, and we will also be at Textile in June. So now I'll give parole to Isabelle de Schrijver from Centexbel, who will introduce the SeaBioComp project. Thank you.
Okay. Yes. Hello, good afternoon everybody. Thank you for coming. First of all, a very brief introduction to the SeaBioComp project. I will keep it limited because my partners will explain you in more detail what we have been doing in the project. So all the results will be presented to you shortly. First of all, I would welcome what are the goals of this project. Let's say we want to develop, like the word is saying, bio-based composite materials. So you can see here what we are looking for. Same mechanical properties, low impact on the environment, and of course we want to prove the durability of those materials, so we will also have a special session on durability of the materials and testing in seawater environment. Of course, we are also proud to work together with all of you as companies. So one of the goals we would also have is to make some final demonstrators, because we want to really change from a petrol-based chemistry to a bio-based chemistry. And I think it's obvious nowadays, if you look at the prices of the petroleum and what happens all in the world, we are very dependent of the petroleum industry, and that's something we want to find some solutions for, becoming less dependent from oil, but also looking at alternative environmental safe alternatives for the composite materials. This is just very briefly a glimpse of what we have been doing in the project. What you see is different methods of production, but I will not go into details. I will leave this up to my partners to further discuss. take some time. Yes, I already discussed. But last, but I think not least, we want to work as much as possible also together with you as industrial partners. And this is just a warm welcome for all of you after this workshop to also reflect on the results and maybe think where in your process, in your product, our solutions could be an answer. So if you have nice ideas for demonstrators that we could also put up in the framework of this project, we are very happy to assist you and to make some nice demonstrators. So keep it also open, think about it, and feel free to contact me or one of our partners after this session and to then contact us again, and we can have a look what is possible with respect to demonstrators. So here you can find also the contact details of me and also of Sarah, which is our communication manager. Also, all the info is on the website, so please feel free to contact us if you want. This very briefly, but I think then we should continue with our real program, and I will just take my notes. So I would like to welcome as first speaker of today Chun-Hei Park from ARMINES. So ARMINES is an association for research and development of industrial processing method. It's a private non-profit organization. And Professor Chun-Hei Park has been responsible in our project for Work Package 1. And we will present you proudly what we have been doing up till now.
Nice to meet you. So my name is Chun-Hei Park. I'm currently a professor at IMT Nord Europe. And in this project, so our school participates in this project as an associated partner laboratory of ARMINES. So let me introduce briefly what we have developed during this project, what was the objective, and the description of our colleagues' presentation today. So I think it is needless to say again the importance of the bio-based materials, because all the partners of the SeaBioComp project from United Kingdom, the Netherlands, and Belgium, France, all these countries are at the Atlantic Ocean coastal. So we have a common issue of the waste of plastic and the composite accumulate in the marine environment. So end-of-life treatment of these plastics and composites are really, really big issues. You can see that some boat and wind turbine blades, which are not degraded itself during the environmental nature. So anyhow, someone says that maybe it can be interesting to introduce a bio-based polymers composite, but the question is that not all the bio-based materials are not biodegradable. But anyhow, another advantage of bio-based materials that it is a really effective way to reduce the carbon footprint and energy consumption. So not only during the service life, but also during the material production itself. You can compare the energy consumption and the carbon footprint between the oil-based polymers and bio-based polymers. You can see the benefit very clearly. So that's why we have developed some bio-based composite materials during this project of SeaBioComp. So what we have developed during this project, so we have developed 3 different kinds of 100% of bio-based composite. And our target was how can you achieve especially the equivalent high performance as the oil-based polymers and composite, and for the easy manufacturing, because sometimes the bio-based polymers manufacturing is very tricky. So the first material that we have developed was self-reinforced biocomponent biofilament. So the idea is that, the basic concept, so we developed within a single filament, we integrate 2 different biopolymers. So outside the low melting temperature biopolymer, inside the high melting temperature biopolymers, especially high TM biopolymers inside in these polymers, all the molecules aligned in the same direction to achieve a high mechanical performance. And then these two different materials are combined into single filament. And then these single filaments are weaved into a kind of a non-woven preform ready for compression molding. This is the first material that we have developed. And the second one, why not we can add again the secondary reinforcement such as flex fibers. So flex fibers, biopolymers, every component are the bio-based polymers. And then another advantage is that due to the high stiffness and strength of a flex fiber, we can further enhance the mechanical properties. So this is a kind of a tertiary composite with two kinds of reinforcement at the same time. And also we developed non-woven preforms ready for compression molding. And the third type of, rather in this kind, we didn't develop the materials, but we developed a new manufacturing process. So you know that for a big component, such as wind turbine blade and boat hull, the common material is glass fiber reinforced Somerset composite, usually made by vacuum fusion and VARTM. So instead of glass fabric, we use flex fiber reinforcement in the fabric form, and instead of a Somerset resin, such as unsaturated polyester, maybe you can use thermoplastic resin, but to decrease further the viscosity, we can use the monomer, which can be polymerized in situ. So this is the third manufacturing process. And then each material and each process are adapted to each application in terms of the product size and mechanical properties. For example, the self-reinforced biocomponent, hybrid, thermoplastic monomer fusion, we can use from the small, medium size, and big part manufacturing. And for the intermediate mechanical properties, better one, and the high mechanical properties for the thermoplastic monomer infusion into flex fiber textiles. So, and then my colleagues, Thomas and Elk and the Professor John Summerscale will present each development of each material and manufacturing process from now on. So I hope you to enjoy this workshop. Thank you.
Okay, thank you very much, Chong-hei, for this nice introduction in what we are going to present to today. So you've seen already quite some applications and some methods we are being developing, but maybe let's go now into a little bit more into detail. And then our next speaker is Elke de Meijer from Centexbel VKC. So Centexbel VKC is, let's say, the collective research institute for the Belgian textile and plastic processing industry. And Elke is working in my research group on plastic characterization, processing and recycling, very specific on topics where bio-based, biodegradable and recycling are coming together and looking at, let's say, the future for circular economy. So Elke, we would be pleased to hear what you have been developing.
I'm going to present you the first step in the production of the composites, being the production of the self-reinforced filaments and the fabrics. So to start, okay. So as Chong-hei just explained, in the bicomponent filament we have a core material and a sheet material. So our core material exists out of a high melting semicrystalline PLA grade, and it has a sheet around it of a low melting PLA grade that is most of the time amorphous. And then it's something like this. You have the bobbin. During the break, you can just come and take a look at it more closely if you want. So this is the first step in the production of our composites. And then with these filaments, we can make fabrics. I also have a small sample with me, so again, if you want, you can have a closer look later on. And it's with these materials that we do compression molding to make a composite. So I'm just going to tell you a bit more about the first steps in the process. Okay, so at Centexbel we have a lab scale or pilot scale production of a mono-component, monofilament line. So we can have different structures of our bicomponent filaments. We can have a core sheet material, that's the one on the left, but we can also have an island in the sea or a side-by-side. It's depending on what kind of application you want, what kind of special characteristic you have needed for your filaments. So for this project, we focused on the core sheet structure. So for those of you who are not really familiar with the filament extrusion, so at the line goes from right to left. So at the right side you have the extruders. So here we have our high melting and low melting PLA grades in our extruders. They go through a die to get the nice core sheet structure. And then we start the production of the filaments. They go through a water bath to cool the material. And then we go over those different rolls to stretch the material. And by stretching it, the polymer chains get aligned. And that gives the reinforcement and the strength of our filaments that we need in the composites. So we did a lot of tests to optimize the materials. And the first thing is that we investigated the effect of moisture. Why we do that? Because we work with PLA. It's sensitive to hydrolysis, so you need to have a dry PLA material before you start. And we did a test depending on the moisture content of our PLA, what is able to reach a tenacity. And here we see if you dry up to 50 ppm, which is really dry, you can get a tenacity of 32 centinewton per tex in this case. Using the same parameters, but with a material that's less dry, you can see a clear drop of almost 10 centinewton per tex if you don't dry it. So for PLA, it's really necessary to dry it before you start. So that's one of the main things you need to keep in mind when using this type of bio-based raw material. And then we started with the bicomponent filament extrusion. And there you can also choose to have different core sheet ratios. So if you have a core sheet ratio from 33/67 up to the other way around, 67/33, you see that if you have a higher core sheet ratio, so you have more reinforcement present in your filament, then you have a better tenacity. You can go as high as 90/10, let's say, but then for the next step, which Xunghei is going to explain, during compression molding, the sheet needs to form the matrix. So if you only have 10%, it's not enough to form a nice continuous matrix. So you need to find an optimum between the tenacity, the strength you need, but also still need to be able to process it further on. So all the other results I'm going to show you will be of a 50-50 core sheet ratio, just to start with. So what we did is during the extrusion, you saw we have ovens, we have a water bath, we have rolls. So we can change lots of parameters. So here you can just see what happens if we change the oven temperature, we change the draw ratio, but you can also change the air velocity in the ovens, the water bath temperature. And so we did this with our PLA, and we did it with lots of different PLA grades. I'm just going to go to the next slide. So here you see all the different core sheet combinations, and we optimize them to get the best results. So you see that the combination of core 1 with sheet number 4 results in the best tenacity and the best elongation. But I want to have some special attention to the third combination. Here we tried using a semicrystalline PLA grade, both for the reinforcement and for the matrix. But there we see that it's more difficult to process it, even though we would expect that we would have a higher tenacity, since you have in both the sheet and the core reinforcement and crystals. But it was more difficult to process them, and if you want to make a composite out of them, you need to make sure that you have a temperature window that you can use, so only your matrix material melts, but not your reinforcement. So a combination of two semicrystalline PLA grades, it's not really possible for the processing into composites. That's why the better results we have are made with a core that's a semicrystalline PLA grade, while the matrix is better to have a amorphous PLA grade. And so after improving and optimizing all the parameters and the PLA grades we used, we need to go to the next step, because with just some filaments, it's really difficult to go to a composite. At lab scale, we wind it around the frame, and it's quite easy, but in production environment, you of course want to have something that's easier than manually winding something around the frame. So the next step is of course to make a fabric. And then here you can see them during production. So on the left side, you have a picture of a twill 4-4 structure. On the right side, we have more a unidirectional fabric. It depends on the application you want, whether you want to have it the strength in one direction or you need it in different directions. You can just take the kind of fabric you prefer, and then you can stack them also to optimize the strength in the direction you want it. But here we had two main problems. The first thing is this is quite a difficult filament to work with to produce the fabrics. It was a bit too hard to work with them, so we need to optimize it that it's more smooth to use it during weaving. And the second thing is we made 3 different fabrics, so a twill 2-2, a twill 4-4, and a unidirectional one. And with the twill 4-4, we saw that during the first lab trials to make a composite, we had some shrinkage of the material. And there were 2 ways to solve it. The first one is to go back to your filaments and to have a relaxation step during the processing, so the shrinkage is already less. A second option is to include a thermofixation step, where we put our fabrics over a frame to fixate it, and then just a small moment, like not even a minute at 80 degrees, and then also the shrinkage is way more limited and easier to use. And that's how we get to the self-reinforced fabrics, so we can use them as a preform to make a composite. Thank you for the attention.
Okay, thank you very much, Elke. We will leave the questions for after all presenters have done the presentation in the session. So keep in mind your questions if you do have them, and we will come back to you after this session. So then I would like to introduce you our next speaker, which is Thomas Laurent from CETI. So CETI, for those who were already here this morning, so you had a nice visit, so you are quite aware what they can offer you and what they can do. For those who are online who did not do the visit, so CETI is a European Center for Innovative Textiles here located in Tourcoing. So they do have different, let's say, prototyping machinery available, starting from spinning, dry lathe, melt blowing, but also recently they also invested in a recycling line. So the whole processing of textiles could be done here. More specific, Thomas is a doctor and engineer in micromolecular chemistry and textiles. He has been working already now for 7 years in textile recycling and mainly focusing on reinforced thermoplastic composite materials. So in this project, they are very specifically working on the flex and biopolymer reinforcement. So I'm quite sure that he will be nicely able to introduce you what they have been doing in this project. So Thomas, the floor is yours.
So thank you, Isabel. Yeah, we are going to. I'm going to introduce you a bit what we have done in CETI, focusing on textile part for reinforcing composites. So a development of textile reinforcing components for the composite structure. So first of all, before starting everything or anything, I would say that we have to choose a good polymer or a good fiber. So I will introduce you shortly what we have made as a study. So complexity, if you are looking on the right side or on the left side, if you look at the front, we have studied several polymers going in several processing and seeing what could be the availability and try to scale what we have. So you have on the right what have been ordered so we can decide what to use. So you have, of course, bio-based products or non-bio-based product, and biodegradable or not biodegradable, and you see clearly that on the right you have PHA, PHB or PLA, but we have focused also our study on the availability of polymers. So we have made a study about bio-based polymer market capacities. So we have tested different polymer, which could be biosourced, of course, because they are not as fossil polymer, but they will not be anymore in the future. So you have the polymer list there: polyester, polyethylene, polyamide, PLA, even for non-woven. If for non-woven, polyamide and polyester could be a problem due to temperature and degradation of natural fiber, of course. But as we have developed many things, I will go through. So first of all, metal spinning tests, of course. So I put some results about different polymers. So for those who were here, they have seen the melt spinning line. So a 3-component melt spinning line, which allow us to make different cross section, different mixing of components, up to 3 components mixing. So there, firstly, we tested several polymer which could be biosoft or not. What's going out from this study in melt spinning is polyamide 11. If we talk about iMelt polymer, of course, polyamide 11 could be the best solution, seems to be the best solution in terms of tenacity. And PLA was quite difficult to process. But PLA, of course, is quite compatible with natural fiber, so you will see after that in a different process it will be better. Sorry, try to move. So we focus first on high melt and low melts, but after making this study, we try to mix different polymer which can be considered as high melt or low melt polymers. So we try different ratio, 40-60, 60-40. You have the results here in terms of tenacity and in elongation. So it's complex graphics, of course, but you can see the tendency. You can also see the tendency. So we try Cauchy island indices structure in melt spinning, and what appears from this study is as firstly PA11 PBS, bio-PBS seems to be one of the most appropriate couple of polymers. But not only, what we have seen also isn't quite a difference in the structure. There is an increase when we draw more, but it's normal. And as they have observed in Centexbel, when we increase the eye melt ratio, we increase also the tenacity, which is quite logical, but when we talked about couple, it's not so obvious. For She-score, so PA11 bio-PBS seems to be the best couple, but not obvious. It's more obvious if you look at the structure of islands in the sea. And in melt spinning, in general, it seems to be more appropriate structure if we look at the tenacity. So after melt spinning, after doing a yarn and study on the yarn, we have passed to another possibility, which was the spun bond process. So the spun bond process is to make filaments through a spin pack, like we do in melt spinning, but for doing a non-woven, it's stretched with air in between before laying on the belt. This is the principle of the spun bond for those who didn't know the process. And we have done the same study as we have done in melt spinning. So we try to study high melt, low melt, and then B components. I try to have the same strategy. So first of all, we try, I don't go on all the study, high melt and low melt, but we try to develop a first grade of considering polyester as a high melt and PLA as a low melt, because there are different temperature. And you have the results here. What we observe is that, for instance, PLA chemistry could play a role, because you see that you have two PLA, different PLA used, 6202 or 6100, and you see that clearly that there are some difference in tenacity, in normalized strength, sorry. So we normalize strength is, we do in both directions of the non-woven, and we try to normalize, so we see clearly the strength of the whole non-woven. This is the goal of the normalized strength. And we clearly see that polymer PLA chemical structure could play a role there. So we try to complexify a little bit the study, of course, because we move to several different couple using PLA high melt, polyester, PLA low melt, and try to combine everything. So you have the results here, all the results here. So we try different cross-section also, She-score and island in the sea. But you could see also the tendency. Clearly, islands in the sea offers in spun bond, contrary to melt spinning, worst results. Compared to She-score for spun bond. We tried different ratio also. So higher ratio, of course, seems to offer better properties. Not with all, because it depends on the weight of the non-woven. But we try to produce the best non-woven for testing in Composites, which was for us some PLA high melt and PLA low melt to go further. So you see that pure biosource polymer could lead to equivalent strength in spun bond. So now we move again to another part, which was the task 1.3. Then we try to implement also, so before you have high melt, low melt. High melt is a reinforcing fiber, low melt is a resin, of course, and we try to implement natural fiber inside. So we use another strategy, which is cardine non-woven. So we try first to choose also the best fiber. So you have here the composition of natural fibers, and if I could compare natural fibers to something, I will definitely compare it to composites. So telling that cellulose is the fibers, hemicellulose is the link between fiber and resin, and pectin, lignin or wax could play the role as resin. So if you consider this as a composite, you will see that more bond you have or more fiber you are, stronger is a composite. So it's the same in natural fibers. So if we have a look at properties, you will see clearly that the fiber which has the most cellulose or more hemicellulose are the stronger fibers, so flax, hemp, and at the second level, jute or kenaf. So that's why we choose flax, of course, as a natural fibers for hybrid textile used for composite. So we use cardine needle punch non-woven. So you have the card as a picture, so you can understand better. So we form a web on the carding machine, and then with needles we try to consolidate the textile. And we use a different, we have the same approach to compare with the spun bond. So we try to compare also with the spun bond. So we try pure PET, pure PLA to compare after. But we try also flax PLA and coPLA mix to deliver for composites. But here what we will see is not a composite results, but it's a textile results. So we could see already what are available on the textile. So it's always, it's also the normalized strength here, and we clearly see that a good amount or a good ratio of fiber is 60% of PLA and 40% of flax. But with the results that we have developed also with ARMINES, we have seen that we have to add other components such as low melt composition could play a role in elongation. So that's why we try to manage also elongation by adding, not us, but ARMINES try to add some low melt fiber, low melt components to add elongation without disturbing the tensile strength in composites. Here it's always on textile. So we try, that's why you have this table to manage the good ratio of fibers and flax. I will go quickly on another part of textile composites, which is just reinforced polymer. So we try to manage also short reinforced fiber compound or long fibers reinforced filaments. So what we do is co-extrusion into a 3-melt spinning line just to make a filament that will be available here. I will try to share in the assistance to show you spun bond, what is a cardine non-woven, what is a filament. So we do a co-extruded yarn coming with a yarn from Safina. We thank Safina for helping us on that. And we coated the yarn with the PLA to try to make compounds or to directly make 3D printing, but unfortunately, the limitation was a low pressure, so we were not able to commingle very deeply PLA in flax. So the cutting was a disaster, and I believe 3D printing will also be a disaster. So we tried to move to another solution, which was to granulate flax fibers so it could be very dosable into a compounding line and try to mix directly with the PLA. Just a short introduction on what is going on now. We try to manage also recycling through different access, because the spun bond is made of synthetic fibers and the cardine non-woven is made of fibers. So we try both routes, which was mechanical recycling and thermomechanical recycling, and the tests are ongoing now. Just I was expecting to have so question, but we will see after. So I thank you for your attention, and we will see after for the question.
Okay, thank you very much, Thomas, for this introduction in the PLA flex fiber reinforced composite. Of course, you have seen this was a lot of work being done on the development of the fibers itself, also combination of flex. I think we can now continue with going more to the composite field, so where we really are looking at the compression molding of all those different materials, and Chun-Hei will introduce us and explain you what we have been doing. I don't think we need an introduction of Chun-Hei because we know him already from this first introduction, so I think Chun-Hei, the floor is yours.
Thank you, Isabel, for the kind introduction. So now we have preforms. We need another step to obtain composite products, the manufacturing process. So all these preforms were developed for the compression molding. And in fact, Centexbel and CETI developed a great number of kinds of different preforms, but we just selected a few of them which can be promising in terms of the mechanical properties and the ease of manufacturing. So in this project, we adopted hot compression molding. And I have to emphasize that in general, so manufacturing of biopolymers, biocomposites are very tricky because the process window is relatively narrow. But in this case, you can see that we have two types of materials. As a matrix, we have a PLA, it was a polymer. As a reinforcement, it is also a polymer, the same, almost same type of a PLA. And the basic concept is that the matrix should be melted into a viscous liquid state for the impregnation process, but the reinforcement should stay as a solid state during the manufacturing process to keep their original molecular state. So the process window in terms of temperature, the temperature of processing should be between the high melting temperature of the first one and the low melting temperature of the second one. So you can see that the low melting temperature is 130 degrees Celsius and the high melting temperature is 165 degrees Celsius. So process temperature should be between these two temperatures. We have a process window about 30 degrees Celsius. And then we selected as mold temperature 3 cases, 145 because 135, 140 was too low to melt matrix phase, and 155 and 165, we selected 3 temperatures. And moreover, what was interesting in this project was that all these preforms, so we didn't need the preheating and pre-drying of preform. So manufacturing is relatively easy because we didn't need the pre-treatment of material. And then in terms of the compression pressure, we adopted a kind of staged compaction. That means we started from the low pressure and increased the compression pressure sequentially, because in the compression molding, one of the common problems is that there may be an excessive lateral squeeze flow, and we can lose a lot of amount of matrix material. So anyhow, as we tested the conventional compaction cycle with the constant pressure, it works also. So the first material that we had tested is self-reinforced PLA. So we tested 2 different kinds of filament with 2 different cross-sections. First one is a core and sheet. You can see it on the top, on the left figure. And the second one is islands in the sea. Very small, high melt PLA is embedded in the low melt PLA. And as a second one, so we compared the 2 different types of non-woven technology, dry rate and spun bond. So we compared the 2 cross-section and 2 different non-woven technology. And you can see that according to the temperature, and you can see the result of a fracture modulus on the left graph and the fractural strength on the middle graph, and on the right, you can see the failure strain. So in general, the common issue in the material science that we cannot enhance stiffness strength and toughness ductility at the same time. It is very difficult. But anyhow, you can see that we could increase stiffness and strength without compromising ductility. So it is very good news. And moreover, optimal temperature was around 145, 155. So you know that the most common composite material for compression molding is a sheet molding compound based on the glass fiber and unsaturated polyester. This SMC material, the processing temperature, mold temperature is around 150. Exactly the same processing temperature. That means you can use the same equipment, the same mold for this material. And in terms of the, if we compare the two different nonwoven technology, we found that the spun bond is a little bit better because the process window was a little bit wider. And we observed no difference between core sheet and island in the sea. So anyhow, we could increase modular strength without compromising failure strain and ductility. So we could obtain stiff material, strength material, and at the same time, it is also ductile. So, and if we tested, so flex PLA, coPLA composite is a kind of a tertiary composite. We have two reinforcement in the same material. Flex is the first reinforcement and PLA is the second reinforcement, and coPLA is the matrix material. And maybe you can ask a question, why we add the secondary reinforcement? So we compared. We keep the same amount in terms of volume, flex plus PLA, and we change the relative ratio between flex and PLA. So in this table, you can see the FP1, 2, 3. So all these cases, flex plus PLA, the volume fraction was 50%. In this table, we showed the mass fraction. And we compared mechanical properties. You can see that on the left graph, left 3 dots are the result of a flex, PLA, and coPLA. On the right, the first dot represents the result of a flex and PLA composite. The PLA, in this case, a matrix. So maybe you can find some commercial grade of a flex PLA composite in the market. So you can see that compared with the conventional flex PLA composite, we could increase modulus and strength, and we could almost obtain the same tensile failure strain. So the result, just small amount of self-reinforced PLA, we can greatly enhance the mechanical properties. And then we can conclude this kind of a tertiary composite is better than the binary composite of a flex PLA. And if we measure the fractional properties, we could obtain almost the same conclusion. Especially you can see the third graph. The first 3 dots are flex, PLA, and coPLA, and the last 4th dot represent the result of flex and PLA. We could improve greatly the ductility because we added a small amount of flex reinforcement. This contributes greatly to enhance the ductility of the material. So, I'm sorry, there is some letters are cracked. Anyhow, the question is, compared with conventional composites, so can we contribute to all these bio-based composites can contribute lightweight design? So it is true that, for example, self-reinforced PLA has lower mechanical property than the conventional SMC. You can see that the modulus is lower and strength is also lower than SMC. But you cannot ignore that this self-reinforced PLA has very low density. So if we design a new product, we always consider a kind of the specific stiffness and specific strength. That means mechanical properties divided by the density. This ratio determines the lightweight performance. If you compare the last two columns, especially the last column is the strength divided the density, you can see that these self-raised PLA equivalent or maybe a little bit better than the SMC in terms of specific strength. So that means we can reduce the structural weight of the final product if we use this material. And if we take a look at the result of flex PLA and coPLA, you can see that specific strength and specific stiffness, both of them, tensile and flexural properties, we could increase greatly specific modulus and specific strength. That means if we employ these flex and coPLA materials, we could reduce up to 50% of structural weight compared with conventional SMC. So this is a really big advantage. We can use bio-based composite, we can reduce the carbon footprint, and we can decrease the structural weight. And the question, the manufacturing, the feasibility, especially the complex part molding. So in general, the big challenge of compression molding is to manufacture with a deep draft angle with a corner where we can frequently observe the kind of wrinkle and low pressure applying applications. So this is the result of the compression molding of using the self-raised PLA, the non-woven prepared by dry layer process. You can see that there is no dry zone, no void visible, and no wrinkle. So manufacturing was quite simple. And we just used the same mold and same compression molding press for the SMC manufacturing. And you can see the temperature range and the pressure range was exactly the same as the SMC compression molding. And also for flex PLA and coPLA, you can observe the difference of the color due to the flex fibers. So anyhow, without any kind of special treatment and the kind of the pre-processing, so no wrinkle and no dry zone, so we could obtain the perfect manufacturing quality using this process and materials. So anyhow, so we can say that we developed two different kinds of 100% bio-based composite preforms compared with the conventional SMC. So we could obtain the significant weight reduction, and then we can use the same equipment and same mold for the SMC. We don't have to develop a new mold, a new manufacturing equipment. And anyhow, so manufacturing cycle, process cycle time are a little bit longer than the conventional SMC compression molding, but nevertheless, it is much shorter than the vacuum infusion and the VE-RTM. And so due to the proximity between the reinforcement and the matrix, because we implement the matrix and reinforcement in the same filament, and the impregnation path was relatively short, and we could obtain the excellent impression quality. And void volume fraction was lower than the 2%. The 2% is almost the aeronautic part grade. And in terms of the drapability, and we obtained no wrinkle formation. So this non-woven preform has excellent drapability. And we are expecting, we haven't tested yet, but we expect that this kind of non-woven preform will have excellent impact resistance because it has good ductility and good toughness. And we are supposed to do some life cycle analysis to prove really this material can reduce the carbon footprint eventually. So thank you very much for your patience.
Okay, thank you very much, John-Hey. This ends up our first session explaining you self-reinforced, flex-reinforced combination of both. First of all, I would like to ask here in the audience, are there any questions for one or, let's say, for all of the speakers here available in the room? Also, people online, you can easily type your questions in the chat if there are. I may start just with one question. I have seen Elken has mentioned the moisture dependence. What about flex and moisture dependency?
We didn't have study this aspect because in terms of for spunbond, for instance, we remove flax for processing. We need also to process flax with moisture. Maybe at the composite part, Cheng-Hei could add something, but at the textile part of preform for us, there is no influences about moisture. We have observed at the textile level, but maybe Cheng-Hei have seen something more in the composites part.
So in fact, in the beginning, we did a kind of the preheating and pre-drying before the compression molding. But what we observed, all these preforms became very brittle. So that's why we directly put all the preform without pre-drying in the mold, and we heat the mold to the compression molding. So maybe even there was some moisture inside the preform during the hot compression molding, so some moisture evacuated. And maybe during the service life, so moisture will influence the mechanical properties such as the aging and the durability. But anyhow, during the manufacturing of composite, during the preparation of the preform and handling the preform before manufacturing and during the compression molding, so these materials were not sensitive to the moisture that we have observed so far.
Okay, thank you. I see in the meantime a question popping up in the chat because we focus mainly on flex fibers. So the question is, have you also considered bamboo? Although it's not produced in EU, but could it be a suitable alternative fiber to flex fibers?
It could be suitable because I know bamboo very well, and it's much more stronger than flax. The problem is the processing actually, because it's not so well developed as some textile engineers knows. So it's not so much developed at that moment, so it's hard to find it on the market for developing such polymer. And as you mentioned, Isabelle, it's not local fibers, so that was not the main objective in the SeaBioComp project, because we're trying to be more sustainable, and develop bamboo was not actually industrial available and not local, so it was not an alternative considered in this project.
So I heard that there was some local production in this bamboo in the South France. And there are some commercial products also. But anyhow, as far as I know, I'm not a specialist of fiber and textiles, but as far as I know, one of the biggest technical issues with the bamboo fibers is the fiber extraction from the bamboo. So maybe it can increase the production cost as well. So anyhow, the bamboo has very specific properties such as excellent elasticity. So it can be an interesting topic, but maybe for the next project.
Okay. If you talk about costs, what about PLA, availability cost of PLA? Because in the beginning I said less dependence of oil, but we know what happens with oil prices at this moment. Also, prices of the polyolefins, the polymers are increasing. What about PLA? Do you see a future there, and what would be the evolution?
we have a discussion just before about PLA with some partners here. So yeah, what we see, we observe. Clearly, I told some price dependency at that moment. PET is increasing. Also, polypropylene is increasing. We are at that moment. We know that PLA is much expensive at that moment, but you have to consider that at a processing level, we have not so much developed compound as we have done with polyethylene terephthalate or with polypropylene. I'm quite sure if we increase the capacity, we will decrease the price. And at that moment, we know that, yeah, polyester are near to 2.5 euros per kilogram for a fiber, where you are at 4.5 for a PLA fiber. So you are less than 2 times. So it's not, it's much more, but it's not a so big issue for me at that moment. And I'm quite sure if we develop so much product, we will decrease the price of PLA.
I think we're all looking forward to the new plant, which has been announced in France. So let's hope by having more volumes of PLA also very soon in the future that also prices will be more competitive. So we still believe in the polymer. I don't know if there are questions from the audience. Still some open issues that you would like to discuss with one of the speakers here in front? I see no hands raised, so if not, then we will have a short break now. So we will invite you to the coffee. I think it's same locations as where we have lunch. And we see each other back, let's say, in half an hour. Also for the people online, there will be a short break. So we hope to see you all back at 3:30. Thank you very much. We will continue the second session of this afternoon. First of all, we will have a presentation on another technique of composite formation, and then we also have a look at durability parameters of our materials, and then we have invited 2 external speakers to continue our program. First speaker of this afternoon is John Summerscale, who is a professor at University of Plymouth, specialized in composite engineering and working for the research groups Materials and Structures, so on advanced composite manufacturing. John Summerscale is a professor for already quite some time. He has been teaching and researching fiber-reinforced polymer matrix composites for many years, and I'm quite sure he's passionate in the field, and he will introduce you in his work in the framework of this project. So, John, the floor is yours.
Thank you. Thank you, Isabel. Apologies if my throat gives up in the middle of this. At Plymouth, we've been looking at the possibility of making natural fibre reinforced thermoplastic composites manufactured by monomer infusion under flexible tooling. And I'm going to try and advance the microphone and do the wrong things, but here goes. This is the project that we're based within. Fundamentally, there are some big composite structures out there, things like M5, the luxury yacht, the Visby stealth corvettes, the offshore wind turbine blades, which are of the order of 75 metres for the ships and 115 metres for the wind turbine blades. And processing thermoplastics at that scale is not trivial. It's certainly not something you're going to build a compression mould to do. So can we make similar structures using a thermoplastic matrix? Why would we want to do that? Because we're trying to make a sustainable composite. There are all the advantages we get from natural fibres and some disadvantages. And if we have a thermoplastic matrix, then it becomes recyclable and we have the potential for high impact resistance. So in resin infusion under flexible tooling, also known as SCRIMP, VARTM, and about 50 other different abbreviations, we make a stack of fibres, cover it with release film, add a flow medium above that and then close it in a bag, and then flow the resin, which becomes a thermoset matrix, into the mesh to produce the composite by drawing a vacuum into the bag and allowing resin to flow down the pressure gradient. The advantages of RIFT are we get a high fibre volume fraction, a low void volume fraction. It's economic for large structures, whereas trying to make a mould tool and keep it together for resin transfer moulding would be extraordinarily expensive. And it's a clean process compared to hand lamination, which has been used for some of the largest structures in the past, because it encloses styrene in the bag, if we're trying to do it with unsaturated polyester resin. But thermoplastics, the melt viscosity is far too high to get it to flow in an infusion process. But if we start from the monomer and make the polymer at the same time as we make the composite, we can potentially do monomer infusion under flexible tooling. In order to do that, we need to pick a monomer that suits a variety of characteristics. It needs to be liquid at the temperatures that we want it to flow. The viscosity has to be suitable for infusion. If it's too low, you tend to trap air. If it's too high, it doesn't get to the end of the product. The process temperature, because we want to use natural fibres, needs to be below 200 degrees centigrade. The use temperature ideally will be below glass transition temperature for ease of design. And if we're going to put it in the marine environment, we want a low moisture uptake because moisture drops the glass transition temperature. There are also desirable characteristics in the context of the SeaBioComp project, that it be bio-based monomer, that the process time is long enough to make large structures, that it's a sensible cost per kilogram, that there is low embodied energy and low environmental burdens, and it's recyclable. So we set ourselves quite a demanding series of constraints in order to make sustainable infused marine composites. We looked at the paper by Van Rijswijk and Bursey, who suggested there's a whole variety of polymers that we might use, but some of them don't meet the criteria we're aiming for. So the reds here process too hot. Some of them have got too high a viscosity. Reds in column 4 process too hot. In column 5, we end up with very limited number of possibilities because of the moisture uptake. And then, is it bio-based or not? Well, we end up with polylactide, but it's got a high process temperature, or methyl methacrylate. And then the next slide, my researcher put advances into this that I hate. Methyl methacrylate, it's an addition polymerization, so there are no co-products. It's a drop-in substitute for the thermoset resin systems. It's a bio-based monomer. As a bio-based monomer, it's not yet commercially available as infusion grades, although our supplier is now producing SeaBio products for other acrylate systems. And material recovery is relatively low in the end-of-life hierarchy because it's not straightforward to melt, reprocess, but you can recover the materials. Just waiting for somebody to contradict me. The lactide is a ring opening polymerization, so again, there are no co-products to deal with. But it's a high temperature process, typically 120 to 180 degrees centigrade, because it comes as a solid powder. It's a bio-based monomer by default, and melt processing is possible in the end-of-life hierarchy. So we're beginning to see that even with our limited set of potential monomers, there are constraints that there isn't a perfect material. We did this at relatively small scale. I won't dwell on this slide. One of the issues we had was temperature uniformity across the mold tool. So we found that using a glass plate between the heaters and the mold tool spread the heat more uniformly and gave us flow that was closer to what we expected. And then we did a pretty comprehensive study. I'm not expecting you to read the numbers off this slide, with a variety of different parameters to try and identify how we might produce the PLA. Based on flexural results, all samples produced under atmospheric pressure using an open mode for the PLA, because we can't infuse the PLA quite the same way as we can infuse the composite. We identified optimal processing parameters of 150 degrees centigrade for a couple of hours, monomer catalyst ratio 500 to 1, and cool to room temperature. and got properties that look reasonable, not special, for a polymer. We then made some composites with the flax PLA and with the helium and got these mechanical properties. At this point, I'm desperate to use the pointer and it doesn't work for those people online or those in the room. But the top line is flax PLA, and the experimental strength only comes out at 60%, and the experimental modulus only comes out at 37%. For the helium acrylic, we're getting sensible strengths as we would predict, but again, the flexural modulus is low. So we need optimization of the in situ polymerization, especially for the flax PLA composites. We looked at the optimization, the time catalyst ratio cooling varied at each temperature, including optimal parameters for pure PLA, and identified that 150 with a catalyst ratio of 500 was given as the lowest modulus and the lowest strength. So there are differences in the air that's affecting the process somehow. And again, the numbers that we've been given previously were given as the lowest interlaminar shear strengths, indicating that the fibre to matrix interface is weak. So the optimal parameters for casting resin are not the optimal parameters for making the composite. The flax PLA matrix samples in the highest temperature batch showed the best properties, which is really bad news because tooling options start to fall away quickly once you go to the higher temperature. And the properties as predicted of the PLA matrix composites are still not good and give a very low interlaminar shear strength. It's interesting that the professor at Bristol, who's done a lot of work with natural materials, is also commonly now saying that PLA is not a good matrix for composites in many cases. The optical parameters don't give the best mechanical properties. Why? Well, the flax fabrics may affect the in situ polymerization of the lactide monomer. The temperatures we're working at, the fibre should be dry, but maybe there is some residual moisture. Pure PLA samples were produced without vacuum, while the composite samples were produced under vacuum because that's the nature of the infusion process. We think there may be a polymerization, depolymerization equilibrium around the process temperature we've been using. And lactide may boil at the flow front under vacuum, and the volatile losses affect the properties. So we looked at backing off the vacuum levels, and it does look like lower vacuum produces better properties. We tend to pull the best vacuum we sensibly can when we're doing thermoset resins, and that may not be the best option for our PLA composites. This particular set of tests, no significant differences in the laminate thickness, dictated by the pre-infusion pressures. Some issues here because, if you want to know the personal information, it's a long story, but it wasn't possible to complete the complete series of tests. Again, low properties implying weak things. So, can we make things? We need to move forward. Where are we going next? Thermal analysis. Our instrumentation died and it's taken forever to reinstall the new system. Beautiful new system. Problems with pipework. 3D demonstrator is pending a mold tool design and commissioning, and life cycle assessment is in the future. So the 3D demonstrator, we made a flax helium wind turbine blade at 1.25 meters length as a demonstrator, but didn't have the system to do the flax PLA. We're expecting the mold tool for the 3D demonstrator, which is a 5G telecommunications system housing to go on marine buoys to provide mobile phone and data connectivity at sea. It fits in a meter cube, sensibly, and but it needs the heating of the mold tool. We'll do that in flax fibres in either acrylic or PLA, and probably with a thermoset matrix as well to demonstrate how it compares. but we do need the heated tooling. The life cycle assessment, we're looking at innovative biomaterials. It's not always the case that the natural materials give the best environmental benefits. So our comparison is to glass polyester or epoxy composites. The framework for life cycle assessment is the standard from the ISO 14040 series of standards. And the goal and scope is still in development, but may include these factors. So in conclusion, the monomer substitute for resin in the infusion process, we can get to work. Acrylic is a sensible drop-in, but it's synthetic at the moment and low in the recycling hierarchy. The lactide is bio-based and melt recyclable, but relatively difficult to process. Life cycle assessment may provide evidence for best environmental performance, which may not align with current public perceptions. Interreg sponsored the project, of course. Thank you for your attention, and any questions at the end.
Okay, thank you very much, John. We will continue with maybe a kind of different topic now, but with a presentation of IFREMER. So IFREMER is the French institute who undertakes research and expert assessments to knowledge of oceans. As this project, you have see it already in the name, the sea is being one of the things mentioned in the name and in the logo. So it means that we also have to look at durability of materials in a marine environment on which IFREMER is specialist. I have the pleasure to introduce you two different speakers. The first one is Peter Davis, researcher at IFREMER. The second one, Mayrin Lagal, material engineer. So please, both of you, I keep the word to all you both. Thank you.
Okay, thank you very much, Isabel. So, in the time available, we'll just give a little indication of some of the things we've been looking at in the project to try and estimate how well the materials which we're developing will hold in a marine environment. The work was done in work package 3 of SeaBioComp, which involves the University of Portsmouth, the Flanders Marine Institute, FLIS, and IFREMER, myself and Mylène. So what I'll very briefly talk about is some of the traditional marine polymers and the approach which we use or have been using in the past to look at aging effects. And then Mylène will talk a little bit about the biosourced materials and their aging behavior. In our laboratory, we work on a very wide range of polymers for use in marine structures. These include, of course, boats, which use a very large quantity of polymers and composites, fishing gear, ropes, signal buoys, renewable energy applications. I think you can see a picture at the bottom here of a tidal turbine blade we've been testing recently in carbon epoxy. And on the right, you can see a sample which we received from an offshore operator of a rope which had been in service. So we needed a couple of meters, and he sent us about 100. And then, of course, we also are an oceanographic institute, so we have our own internal applications, which can involve elastomers, syntactic foams, and a whole range of other materials which have to last between 2 and 20 years at sea. So there's a number of aspects which we look at traditionally. Water ingress is the obvious one. UV exposure for surface applications. Biological effects can be quite severe. Mechanical loading is always present. And the difficulty in trying to predict the lifetime of these materials is that these different aggressions generally work together in groups. And so we get mechanical loading plus water ingress, and there may also be UV and biological effects as well. So we're trying to develop the tools which allow us to couple the different approaches. Up in the past, that would have been where we'd stop, but with the increasing concerns about plastics in the environment, there's also a number of other aspects which we now also have to look at. These include microplastic formation, ecotoxicity, and in some of the applications we're looking for, we're trying to get biodegradation. And one of the problems we have is that there are very few tests, in fact, to evaluate these different types of degradation under realistic conditions. So in many cases, we also have to try and develop the test protocols. But I won't talk more about the last three today because it's really the area where VLIS, the Flanders Marine Institute, has been working. So they have produced a lot of interesting results, and those are available on the website. So please, if you're interested, don't hesitate to go to the website and also to contact them. So I'll just concentrate on giving a couple of examples of the sort of results which we expect for the traditional marine materials. So this is a marine epoxy. We have seawater aging tanks, which are at different temperatures. They're continuously renewed to try and avoid some of the biological effects. And we monitor them continuously. And essentially, we put samples in and we look at their weight gain. And that gives us an indication of how quickly water diffuses into the materials. So here we have an example where we have three temperatures. At 60 degrees, after about a month, the sample is fully saturated. The water level is stable. At 40 degrees, it's just getting there after about 4 months. And at 25 degrees, it would take probably about a year. So this is one of the difficulties also is these tests are long. And so it meant that within the project, we had to start our aging very early. And so we started on one of the original materials. And so what Mylene will talk about in a minute is some results from some of the original self-reinforced PLA, which was available at the start of the project. So what if we have water in the material? Well, one of the things we see in the traditional materials is that the modulus drops. In this case, for this marine epoxy, we've lost about 30% of our modulus after when we've reached a saturation, which in this case would have taken probably a few months. And the strength has dropped for about 50%. So that is the immediate effect of what your properties of the material, how they've changed when it's working in water. But the good news is that for these materials, it's a reversible change. So when you dry them out, then you can recover most of the modulus and most of the strength. So it's a plastification effect rather than a degradation effect. If you leave it longer time, then you'll start to get degradation. And it's also not a lot of comfort if your material is left all the time in the water to know that if you took it out, you could get some of the properties back. And so that was the short-term properties. And then just an example of what happens for long-term properties. Again, this is not easy to describe without a pointer. What we've done is we've done creep recovery tests on an epoxy material. We did them first dry. So those are the square blocks, or the rectangular blocks are showing the stress. So we increase in stress for an hour and then unload for 3 hours. And then the colored lines are tests which were done after aging to different degrees of water ingress. So the first one is after 55 days in water at 25 degrees, and then the last one is after a year and a half. So here we can see we have at low loads a pretty elastic behavior, but gradually as we increase the loading rate, we get a bit more viscous behavior, creep. And the creep response, which in the last column is the little red dashed line when we have no water in the material, has gone to the green line when it's been in the water for a year and a half. So the viscous behavior is strongly dependent on the water in the material. So that's another effect which you have to, if you're looking for a long-term application, this could be the critical loading case, and you have to try and predict that as well. So how do we do that? Well, for that, I'll pass you over to Mylene.
Thank you, Peter. So to include the environmental parameters in a predictive framework, there is several approaches. In the lab, we use 3 of them. So the first one is a mechanistic approach. So this approach will need a deep understanding of the chemistry of the material. So it's a quite complicated approach, but it can be done. Another one is a fully coupled approach. So you have seen on the previous slide with Peter that there is a lot of different possibility of coupling for aging. So here in that approach, we'll try to combine all of them depending on the application and to really predict due to that with a good understanding of the application. And in the project, we have used the semi-empirical approach. So I will explain you a little bit more. So basically, we put the samples in water, in seawater, and see what happens. But to give you a little bit more understanding, we will do a first step. So the samples are immersed in natural seawater, and we will do a gravimetry test. So we will weigh the samples regularly, and like that we will get a weight gain, and it will help us to model to do a model of the water diffusion kinetic. And this will give you the water profile in the structure, which is, of course, absolutely necessary when you want to do a prediction. Another step, what we are doing is to test the different properties of the material. Yes. So we will test the mechanical properties, chemical, physical properties. We will, at a long time, of course, during aging. And with all these results from the different characterization, we'll try to correlate all the results together to try to understand what's happening in the material a long time in the sea. And then when we have this understanding of the change in the material, we will correlate these properties, this result, with the moisture content, with the water diffusion. So we'll mix the two steps together in order to have a prediction. So it's what we have done in the SeaBioComp project. And yes. So here's how the materials that have been tested, and they have been well presented before, so I won't go back on this. But if we took one of the examples that has been presented before, it's the self-reinforced PLA. So PLA, it's a really good candidate when we are talking about bio-based material, because it's bio-based first, it's recyclable, but one of the problems is that the bulk polymer tends to be brittle, and this can be a big issue for marine structure. So one of the ideas was to do self-reinforced PLA and to use the properties of high elongation of the fibers in order to improve ductility. And on the graph on the bottom here, you can see the stress strain curve of the self-reinforced PLA, and you can see that it's a ductile material. So it's this way as of introducing PLA fiber in PLA matrix has allowed to improve the material. And here you can see a picture of the structure of the material, the structure of the composite. And now the question, how this material behave in seawater. So here you can see different graphs. So on the first graph, on the top, you have the weight gain in function of the square root of time. We have used this scale due to the diffusion law. But so what we have done is the immersion at different temperature in natural seawater. So from 4 degrees, which is the temperature in deep sea, up to 80 degrees C. 80 degrees C and a lot of different temperature in between was to perform accelerated aging tests. And as Peter has shown you before, it's necessary to perform accelerated aging tests usually in order to understand the behavior of the material in long term. So here on this graph, you can see different behavior. You have a behavior above 40 degrees C. And you can see with a fast drop of the weight gain follow with the drastic drop of the weight gain. And below 40 degrees, you can see a Fickian behavior, which is really stable. And you have, again, another behavior at 40 degrees, which is a mix between the two. And so when we have seen that at low temperature, the material was really stable. So here we are up on the weight gain graph, we are up to a 1 year test. We have done some mechanical testing. And it's a second graph on the bottom. So you can see it was tensile test, and we have performed for samples immersed at 40 degrees and 25 degrees. So you can see here the maximal stress in function of the immersion times in weeks. So in blue, samples immersed at 40 degrees, and you can see that at the beginning, in the first weeks, up to several weeks actually, the behavior was quite stable with a slight drop, but not drastic one. And then a drastic drops, which correspond more or less to the increasing of the weight gain. So the last point at 48 weeks immersion time correspond to the higher weight gain on the curve. At the opposite, for 25 degrees C, the tensile stress properties was quite stable, even after 2 years of immersion. So this was the basis for the lifetime prediction. And on the same way, you have seen that natural fiber composite have been tested also in the project. And one of the problems with this material is that the fiber is very sensitive to water. The question has been asked before, it's very sensitive to water. And when you immerse samples like that, the side of the samples, the edge of the samples, are cut, which means that the fiber is directly in contact with water, which is very severe. And it's, of course, not occurring when the material is used for the different application. So what we are doing in the laboratory is to use this kind of water tank. So you have two pictures here, and so we put natural seawater in the tank, and you can see that there is different holes in the side of the tank, and that we can seal the samples on the hole, which means that the water is only in contact with the side of the samples. And the result for this kind of test is that if the matrix protects the fiber, if it's well around, then the properties rotation is really good, and there is no problem with this kind of material. And this has been verified with several examples. That there is many other examples, and one will be presented at the end of the day today. But here we have presented some of them. So you have the Gualas, for example, from Keros, which is made with flax composites. And it's on the sea since 10 years now without any problem. So you can see that it's possible to use flax composites in marine environment without any problem. You have two other examples, one from Merconcept and one from IDB Marine, which commercialized different boats also made with flax. So we will see another examples, as I say before, for the last presentation. So to conclude for this presentation, there is more and more polymers and composites that can be considered for marine application, and particularly bio-based materials. And those materials are really interesting. And as an example, self-reinforced PLA may provide an intermediate solution due to the fact that its properties are between the bulk polymers. We have seen that it has been improved, and between the glass fiber composites. And of course, there is the advantages of the recyclability here. And for the flax reinforced polymers, they are already in used in marine environment, and the experience is very positive about them. So thank you.
Okay, thank you, Peter and Mylène, for this presentation. We will come back to it with questions afterwards. We will continue with the program, and our next speaker is Frederik de Splenter from KU Leuven. So KU Leuven is a university located in Belgium dedicated to education, research in very broad fields, let's say more than 15 faculties they have. Today, Frederik is presented here. So Frederik is professor in the domain of polymer processing, and he's head of the research group Propolis, which stands for Processing of Polymers and Innovative Material Science. And today he will also talk about flex composites. So Frederik, the floor is yours.
Thank you very much, Isabel. Good afternoon, everybody. So today, a short talk about fully bio-based and degradable injection-molded thermoplastic short fiber composites. So a full title, some explanation about this. So as already indicated, Propolis, some background. Okay, maybe not all of you know us. I will not take it too long. Some background information, what we have been doing on biocomposites. We are already doing research in this domain for more than 10 years. And let's say we also focus on different composites. I want to show you some comparison for local composite materials and also from less local ones, and some time for conclusions and questions. So just some background information. Okay, group located in Bruges, so KU Leuven is all over Flanders. Of course, Flanders is not a large region in Europe, but KU Leuven is well distributed all over Flanders, and we are in fact located in Bruges, so quite close to the coast. So also other people from our campus are dealing within this Interreg program. So in my group we are about 20 persons, and rather recently we even came closer towards Centexbel, where Isabel is working, also closer to this region. So we are also located in this circular materials center, on which also strong focus is on, let's say, sustainable material or process development, so in a strong partnership. Okay, so what's our main thing? So maybe university, all people think this is always fundamental research. So I'm in fact belonging to the Faculty of Engineering Technology, so not engineering science. So I'm, let's say, collaborating quite a lot with industry in trying to do the translation from fundamental research towards applied research. And in that way, I'm using a lot of, let's say, basic material characterization tools, not the full advanced ones. I have access to this equipment, but all the pictures which are here are available on our campus. And to support the next step in my, let's say, one of my main topics within the research group in this, performing numerical simulations, not to go for the trial and error approach. So, okay, let's say basic material characterization to see what do we have to put into numerical simulation tools, and also to see what's the performance of materials. So as indicated, we have a strong tradition to go for numerical simulation. So for the different processes for polymer processing, ranging from compounding, injection molding, extrusion, thermoforming, we have numerical simulation tools available, and most of them are able to process or also to cope with fiber fillers to see what's going on. And so numerical simulations, in a lot of cases, it's trying to look for pressures, trying to look for temperatures as function of time, and to see what's the behavior. And maybe, and for sure, if you have bio-based materials and thermal sensitive materials, maybe we have to take into account the sensitivity to high temperature loading. So that's also current projects going on in that domain. So numerical simulation, so that's a second part of main focus in the research group. And then the last part is also to compare numerical simulation results with real processes. So we have quite some equipment available in the labs which are highly instrumented. So really to be able to measure which temperatures and pressures are present inside the mold. In fact, I'm less interested in the product which is realized, but I really want to compare it with what type of prediction do we have there, and does it correlate well? And of course, engineering work starts if it does not correlate. Why do we have something different measured than which was predicted? So we do so for compounding, injection molding, and extrusion. Okay, so just an overview of different projects which are going on. So we are not only dealing with bio-based materials, but as I am a mechanical engineer, so we try to understand the whole thing of processing of bio-based materials, recycling of PVC materials, recycled polyolefins, also all other types of, let's say, polymer processing are investigated. So, but main focus on thermoplastic materials. If we have a look on some history about biocomposites at KU Leuven-Bruges campus, so we are mainly focusing on short natural fiber thermoplastic composites through injection molding, as I also have colleagues in Leuven itself. So Professor Ignace Verpoest is maybe well known in this consortium. Of course, he already retired, but he's still active in the field of natural fiber composites. So he already has maybe 30 years experience in processing on long fiber, natural fiber composites. So we have some subdivision there. So at Heverlee, Art van Vuren, together with Jan Evans, they are focusing on long fiber reinforced materials. We are focusing on short fiber reinforced materials. So in 2011, we had a coordinate project in which also Centexbel was involved, this Flux Plus project, in which we tried to put short flex fiber reinforced short flex fibers into polyolefin matrix, so and to see how this can bring some extra material properties. So later on, there was this Valor Flux project, so to commercialize this type of compounds which are developed, because a kind of market push is difficult. And you can show to a company, we have some nice material, and show them some tensile bars, but people will not buy this or will not use this material, and for sure not use it if there are some variability in properties. And polymer processes or polymer processing companies, they are kind of addicted to their initial materials. So, okay, it's not 2006, okay, the start of setting up this Interreg project. So Athens is a project which is run in collaboration with the people from Début. So it was initiated 2016, and in that Interreg project, so Flanders, Walloon region and northern of France, we are focusing on, let's say, combining natural fiber reinforced materials. So trying to weld them together and or to apply some adhesive also to combine them. So in this project, there is a focus on flex fiber reinforced PLA materials. 2019, there is a collaboration with Ethiopia. So KU Leuven University and universities of Ethiopia are collaborating. And I have two visiting PhD students, and both of them brought some fibers with them, natural fibers. So I set up a kind of competition and to end up with the highest mechanical performance for, on one hand, PLA with flex fibers, PLA with NZ fibers, or PLA with sisal fibers. Some results will be there in some future slides. Now, since last year, we also have this Repla Flux project in collaboration with Centexbel. So the main aim is also to use flex fiber to upcycle polyolefin waste stream materials and also PLA materials. Some pictures, if they want to pop up. Okay, the main reason is maybe this movie. So as also already showed or indicated before, let's say in compounding and generating this type of compound for the standard thermoplastic processes. It's not that easy to get your natural fibers nicely distributed into a thermoplastic material. So in one or another way, they have to be as flowable as possible and not to stitch together and not to be too bulky. So, but okay, seems this work. And so based on this expertise, which is there for more than 10 years now, we of course still investigate also how to improve, let's say, fiber orientation, how to predict this local mechanical property. So this is the whole range going from top left to the right, where we start from the compounding over the injection molding into a plate, in which we still have some prediction of fiber orientation and also some local properties. So on the top right, we have some X-ray micro-CT pictures in which you also can see how this flex material is distributed. So with this type of material, so originally it was polyolefins reinforced with flex. This of course changed towards fully bio-based ones and to go towards PLA reinforced with the flex fiber. Of course, it was already mentioned before, PLA is maybe not the best matrix material as it's really brittle. So in that way, also some plasticizers are used and it's already possible also to go to things which are close to fully biodegradable. So some other types of application are already developed as indicated on the top right. We have some commercial products, so left and bottom left we have some plateaus, okay, or plates which are used in catering companies. So over there, okay, let's say they already used also the flex fibers to have higher mechanical performance. Other developments is also the 3D printing. So with this filament 3D printing, as is shown in the middle. So also this is a flex fiber reinforced materials, and okay, let's say this went quite well. Another process which is used is this rotational molded, but this is still a polyethylene flex fiber reinforced chair, so it's kind of design part. To be honest, okay, the contribution of the flex fibers in here is not too high for the mechanical performance, it's more a visual effect, but it's, yeah, okay. It has a kind of soft touch jeans feeling, and that's the argument to sell this type of chair. Okay, so what's the whole thing? Of course, to generate this compound, we have the matrix, starting from this polyethylene or polyolefins, and to add these cut fibers. So to cut these flex fibers into a controlled length and to get it nicely compounded is indeed really the main challenge. So to cut it is challenging, also the dosing is challenging, because cutting this natural fiber is always a lot of wear into the knives and to cut it in a controlled way. And of course, we also have some contradictions, so limited processing temperatures due to the natural fibers results in high pressure, so, but some nice applications are there. Also, small boxes over some transportation solutions and even hoses for fan applications. Even some thermoforming was also possible to do with these natural fiber reinforced materials. Okay, so just some properties of this short fiber reinforced PLA materials. So if we go for the neat PLA modulus of 4 gigapascal, so if we go for 5% and up to 20%, of course, we see some differences, longitudinal and transversion direction. So also there, we see some improvement of mechanical properties, but not as you would expect from the theoretical situation. So also due to some yet unknown behavior, let's say, within this flex fiber or interfaces. If we go for the strength, then we see it's getting down. So that's of course not that nice, but we have to choose, of course, depending on the application. Do we want to have a kind of increase in stiffness, or what's the main request from the application? So we of course also control the orientation of the fibers in the plates at different locations. This can be done using X-ray micro-CT and can be compared with this numerical simulation result. If you also have a look into the top right picture, it's not only fibers, but also some sheaves are still present in the type of material which is used in this type of applications. So that's the PLA flex composites. Later on I will compare all of them. So that's first one in the competition. Okay, before we go to the second one, also type of work which is done in our research group within the framework of the Athens Interreg project is, for example, is to model the whole behavior of a natural fiber reinforced material. And this is now using a adhesive, and just to see what type of stresses are occurring, and taking into account the local fiber orientation. So not assuming homogeneous properties of the two materials, but in that way you can see how these stresses are developing in the whole joint there. So of course, you know, towards the end of the parts which are glued together, you have some higher stresses. But in this one, we take into account also local orientation of the materials which are joined together. Of course, this can also be done as soon as we have a kind of idea of the laser welding done in the research group of Professor Park. Then also stresses can be calculated. Okay, if we look to, let's say, these sisal fibers used to reinforce our PLA, then, okay, at first some measurements were done on, let's say, the strength of these fibers. So, and this has been done using DIC in the research group of Aart van Vuren in Leuven. So they did single fiber testing and have a look for which is the potential of this type of fiber. So that's the PhD work of Ishiti Kashen. And only results are there for 15% of fibers. We also have to deal with a completely different cross-section of the fibers. It's kind of C-shape shape, and also the diameters are quite large, so it's more rough fibers. If we look to properties, so we end up with an average tensile strength of 44 megapascals, really brittle behavior, only 1.6% of elongation is possible, and a E modulus of 4.3 gigapascal, so only slight improvement compared to the neat PLA. Of course, also the idea was there to use plasticizer to avoid the too brittle behavior of these materials. Another material that has been used is this NZ fiber. So this is a kind of banana leaf fibers, and there, okay, also the amount of fibers has been changed, and you see a nice increase. Well, not an increase. On the right side, you have the pure PLA. On the left side, then we added 6% of plasticizer. You, of course, see a decrease there, but then adding again the fibers, you see a possibility to tune the properties over there. Looking to the modulus, so you can see also a serious increase of adding the fibers in there for this NZ fibers. Okay, so what is also checked, that's the water uptake as function of time. So if we have the pure PLA, we can compare it with the different amount of fibers, then you can also see it's really sensitive to water or the humidity. So what is the potential of this NZ fiber? So you can look for a kind of optimum percentage of plasticizer to get to, yeah, depending on the application, and to tune your combination. Also, as stated already before, adding all these, yeah, let's say additives or strange components into your PLA can also modify your crystallization behavior. So that's, of course, also influencing the whole chemical behavior of your material. So if we just simply compare them, okay, this is a story which fits well to, let's say, local processing flex companies, and we end up that the flex has the, okay, let's say, the best performance, or has the broadest yeah, applicability in certain applications. So you can okay, develop different things, but still a lot of things has to be developed. So this PLA for sure is a brittle matrix, so to use it as a pure matrix material is challenging. So, okay, some conclusions. For sure, lots of interest in this fully bio-based composites, and trying to understand what's going on and trying to predict it, not only just doing trial and error on equipment, but trying to understand what's happening inside numerical simulation tools. That's challenging for us. multi-scale fiber properties, and because I indicated briefly, and it's not only pure fibers which are added inside. So sometimes you have a composite inside a composite, and trying to model this in a mechanical way is challenging. So because it's not written on the fibers, what's the amount of fillers, what's the amount of fibers, and what's really in there. Adhesion with thermoplastic matrix, also challenging. So polyolefins, that's not the best thing to be glued. Also, to control this short fiber length is challenging. So compounding, large scale, challenging. And of course, also not that wanted in the industry is, let's say, if you have variation of properties, this is not something polymer processing industry is too much in favor. So, and seems, and it's already also proven by this afternoon, flex fiber, there is a lot of research going on in this flex fiber, but ending with this slide, seems there is still a lot of things to be investigated and researched in collaboration teams. So thank you for your attention and questions, of course. I'm trying or volunteering to answer.
Okay, thank you very much, Frederik, for indeed showing us some nice possibility, but also some challenges. And to end up the session of today, I think we have also invited an external speaker who thinks about innovative materials, and that's Paul Riesen from Greenboats. So Greenboats is developing innovative products, trying to put also added values for their customers, and not only focusing on cost, but also performance and sustainability are very important properties for them. Paul Riesen has a specialist in naval architecture and ocean engineering, simulation, manufacturing and design of natural fibers, reinforced materials, and of course also focusing on processing of recycled materials and product development in highly loaded hydrofilms. So I think after the small music we will hear, Mr. Riesen, the floor will be yours.
Yeah, hello. Unfortunately, I can't be with you, but and the internet connection is very bad. So, but probably if the connection breaks down again, then we may meet at the Jack next week. Hopefully, yeah. So. Who we are, who are we? We are located in Bremen, in the northern part of Germany, and a small team of handcraftmen. Some engineers who do the research and development. That's for example, from my side, I coordinate our research projects, and we have a small engineering team. Focusing on the materials and but also like do the calculations or like FEM analysis, yeah, and just if we have a laminate schedule, we also need to draw the laminate schedule and so on. What do? We are specialized on structural components. That's our main focus, and the maritime environment, and also beyond. And the normal way to look at such a product is to take the price and the performance into account, and we created these third axis measured by LC and an LCA analysis, and based on our material database with different material combinations, we are able to do also small steps if the customer is not able to pay the highest price, or and we are also not dogmatic. If a small step for sustainable is for us a good step, and yeah, so that's how we work. We try to find the sweet spot for each customer. Yeah, I would like to talk to you today about the challenges and the opportunities we are facing, and there are some words like it's like the bio content. There are some other topics like recyclability or the high level of processing quality which is needed on our production side, the price, which is a problem, still a problem. Yeah, it's a problem, and the environmental relief effect, which is our focus to have this as much as possible. And I will start with an example for the bio content, where we were facing the challenge from the team, the 11th hour racing team, the sailing team, offshore sailing team, and they asked us to build the escape hatch you're seeing here on the top, on the left, the top. This small picture, and usually these parts are built out of carbon fiber, and we also had to survive the load case, like of 1.5 tons, and by optimization and also by putting tapes on, like optimizing the direction of the fiber, but also by putting tapes on a certain part, and we managed to be even lighter than the carbon fiber hatch, which was built by the sailing team's shipyard. And yeah, so why did we manage to do so? Of course, because we had the handcraftsmen who were able to build exactly according to what I calculate or in theory, and of course the optimization tools quite helpful, but also the low density of the flex fiber. So these hatch is made out of flex fiber and epoxy resin, bio-based epoxy resin, and is now cruising on the ocean. For the bio content, these are values here, like these are our shipyard or yard internal material properties. And if you look on the top left, you find flex with an epoxy. Of course, as we know, it's not as stiff as glass fiber and carbon fiber as well. But why did we manage also to have these or to build these hatch and survive the load case? Is because if you look at the specific stiffness, we achieve already stiffer. We are already stiffer than a glass fiber epoxy combination or composite, and of course everything above 60% fiber volume fraction is theoretical, and also below 20 or 30. These values are then theoretically, so that we are between 30 to 60% of fiber volume fraction, and the
It seems that we have lost connection, so just wait maybe a moment that he will try to reconnect. Okay. In the meantime, maybe we can continue with if there are any questions from the first presentations we have seen. We will see if we can try to reconnect, but otherwise we will go to the questionnaire. I see a hand raised by John Hay. Microphone. Just one moment.
Thanks for the nice talk, John. So, In fact, during the project, so we have discussed the wettability of helium and the PLA resin with the flex fibers. So can you make any comment on the wettability of the flex fibers with these resins? And do you think really if we need a special fiber treatment to improve wettability?
Thank you for your question. I think the key to what we're doing is that the interlaminar shear strengths are showing very low values, translating through into poor modulus and pure strength. So we don't think we've got a good combination at the interface. In the first instance, the acrylic, we might expect a vinyl silane to work with the unsaturation in the acrylic to give a better bond, but we're just using fibres as provided without a specific surface treatment. In terms of the PLA, I think there's a need for a very different coupling agent. That whatever fibres we use, the epoxy coupling agents, the vinyl coupling agents, there's no reason why they should form a good bond with the natural fibres. With the polyester. The coupling agents that are used with unsaturated polyester resin are very much dedicated to forming a bond with the unsaturation in the polyester, which isn't there in the polylactide. There's no reason to expect a good bond, really.
So eventually, the currently is the helium. We don't have no commercial biosourced grade. Maybe they will develop the biosourced grade. So if they develop a biosourced grade of helium, in terms of the wettability, maybe it will be more promising than the PLA. So.
Sorry, I didn't catch the question.
Oh, yeah. So as far as I understand, your comment is that the improvement of wettability between the PLA and the flex can be complicated. So in this case, maybe the biosourced PMMA acrylic, such as helium, can be more promising than the bio-based PLA in terms of the wettability.
The helium acrylic system, which we're polymerizing, has got double bonds in it, which will react with a vinyl coupling agent. But the polyester system is just inert in terms of the coupling agents that we traditionally use in composites manufacture. Unless anybody knows better.
Okay, thank you. And I have another question to Frederick. So you showed some result of what was the name of the new natural fiber? NSET? Yeah. So could you remind me of the Young's modulus and strengths of these fibers? I don't remember it. Yeah.
I don't know them by heart, but okay, I for sure can provide this data. Later. So, but let's say this type of, they are not that far away from the flex. Okay, somewhat lower performance, but they are available in huge amounts in Ethiopia, and that was the main thing to look for it. But in general, they are larger dimensions, so not that easy to process. But they really want to compare it with, let's say, well-performing material. So it's the thicker fibers, so and also. Less performant a little bit, but I don't know the numbers by heart.
Anyhow, so, is that your own data, or you took it from the literature?
No, this is own measured data. This is measured by this student, so some parts in Ethiopia, but also some parts in our labs.
So how did you measure it? So by single fiber test or the...
Single fiber tests, yeah. So with DIC, so they applied 2 Tipex drops on top of the, on the fibers, and then on a mini tensile testing equipment, they applied the loading and went for the properties. Of course, yeah. It's still challenging to do this, so to stick it on a paper and do this single fiber test. So as a test has been developed by the team of Professor Van Vuren and also in collaboration with Inias Verpoest.
Okay, thank you.
Okay, thank you very much. Frederik, maybe another question for you. So you showed different examples of fibers. We talk about sustainability. If you talk about banana fibers, sisal fibers, whatever that's not available in Europe, what's your thought about? Should we focus really on flax that can be cultivated in our own European region?
I think indeed we should focus most on our local fibers. Of course, this development, those 2 PhD researchers go back to Ethiopia and they want to develop it over there. Of course, it's nice to see some similarities or approaches which are developed, but I think, still lots of possibilities in the flax, but we are not yet there with the compatibility with the fibers and let's say also in the long fiber research, lots of things are going on, trying to get it closed to avoid any or influence of humidity and things like that. So that's, but yeah, also different weather conditions, so freezing, it's changing dimensions, interface properties which are lost or diminished or going down really fast. That's challenging.
Any other questions from the audience? Then maybe just one question for people from IFRIMER. We have seen sustainability is important, microplastics. Do you have some general ideas? Do you believe that our biocomposites will be the future for all, let's say, plastic soups, problems that we are facing with?
It's a really complicated question. I think one of the difficulties is that in order to, when you look at any of the biodegradable so-called polymers, before they degrade completely, they have to fragment. So they do have to produce microplastics as part of the process of biodegradation. And the question is really the kinetics and where they go afterwards. And it's so environmentally dependent. And there are so many parameters. We're assuming fishing gear is maybe going to deep sea. So if it's a coastal fishing, that might be hundreds of meters. If it's off coast, it may be 1,000 meters. And the organisms available are very different. The temperature's different, the pressure's different, the salinity is different, the oxygen content's different. So, and then the effects of all these parameters also on the polymer, but also the life, which is living at those depths, is different. And so the ecotoxicity tests which you want to be doing will also be different. So it makes it we see results coming out for certain specific cases, such as sea urchins is one of the standard tests, which is gives you some indication for some products in some conditions. And that is, at the moment, all we have to go in. And so we have products like as PLA, which we know is compostable, which can be completely biodegradable under some conditions. And the conditions which we're interested in for the marine application today, we don't know. So initially we were going for the durability. We want this to last as long time as possible, and then to be able to recycle it. That's great. I think we've shown that for applications at 25 degrees, we have now samples which have been in the water for 6 or 7 years, and they're still integral. So that's good. So it can last a long time. But when it does reach its end of life, it's still a really grey area. And I think that's where the work is needed.
Yeah, I think so. Because we also receive a lot of questions on tunable biodegradability. For some applications, indeed, it would make sense to have it as fast as possible. For others, we want durable applications. So finding the the best solution for all application. I
Yeah.
think that's still indeed one of our major challenges here today.
Yeah, I think they're wonderful material science problems because you have to have durability for a certain time and then complete biodegradation. So that is your perfect case. But today we're a little bit back from that. Yeah.
But we do need to stop it getting into the ocean in the first place.
That's
we
true.
need to social education and governance that says your waste treatment plant doesn't leak things into the environment.
Yes, fully agree. Any other question? I thought Piet, you had another question.
It was just a
or
comment
remark.
on the bamboo, which the question was asked previously. And I think we have done some tests on bamboo from Covatex, which was their strips of bamboo, which are very natural products. And the properties were very nice, and the seawater resistance was also very good compared to other products, even such as flax. It does resist the marine environment. Okay. It is very sustainable. It grows very quickly. It grows even in Brittany, so it is available in France, and they are sourcing in the south of France, I think, now. So it's starting to come on the market, and we've recently done tests for some racing yacht applications where they're starting to look at it for maybe some aesthetics. It's a lovely material to look at, but also because they're now in the IMO rules, they're putting a bonus on using sustainable materials. So even for racing yachts, they're starting to see some applications. So I think more applications we see, more we get the experience back, and more it'll be used, and the price will go down, we hope. So.
Okay, thank you. Any other questions from the audience or people online? No, I just checked. No, we couldn't reconnect with Paul Reason. So we apologize for that one, but we will share afterwards due to our website. We will share the presentation so you can have a look. And if you have questions, we will also share the contact details of Mr. Reason. So if there are specific questions from him, I would ask you to write him an email. Or, as he already mentioned, next week is the JAC Symposium in France, so you could also visit him there. Then I think if there are no further questions, the only thing that rests me is to thank you all, people here in the audience, but also the people online. Thank you for following this workshop on SeaBioComp. I hope we have inspired you a little bit. We have shown you different ways of production of biocomposite materials. You also have seen that we have some nice results, but there are also still some challenges. But I think we can only solve these challenges if we all work together. And I think we have some nice people here in the room, but also nice people online. So together we can maybe build some sustainable materials for the future. And let's say it's more sustainable, more environmental friendly, and more bio-based. That will be the focus, let's say, of the next coming years. So thank you all for being here. We are reconnected. Okay, then we will give it just another trial. I just received some message that you're reconnected. So let's try again if we can still continue your presentation.
Where did you stop? Did I stop?
I think it was on the slide where you made a comparison of the materials, the carbon fiber reinforced and compared with the flax.
Ah, wow. Okay, I finished the presentation already. I didn't recognize that. I was disconnected. Oh, okay. Yeah, I don't know if you have time.
We still have time, so I think if you still want, we are pleased to have your presentation continued.
So I stopped at this slide?
No, the one before, I think. Yes, on that one, yes.
Okay. Yeah, the main thing, I mean, I wanted to tell you that there are applications where it's easy to replace conventional composites, like this flex epoxy combination for sandwich structures is quite powerful. But on the next slide, you see a comparison where carbon fiber is aligned perfectly with the forces for the forestay chain planes on our flex day sailor, and then to replace such composite, you end up with a lot of epoxy resin, which is still not fully bio-based, and then it's also does not make sense anymore to use natural fiber composites. So we try to work on recyclable carbon fiber or bio-based carbon fiber, but on all of these alternatives, you have always higher energy consumption. And I think one good way to go would to increase the bio content in the epoxy resins. So maybe I do not concentrate on the moisture and mechanical performance and resource consumptions. Recyclability is also a bit, because there's not so much time anymore. But for me, what is important to say is that what we did the last 10 years is that we try to show or try to close the performance gap and to show that it's possible to build natural fiber composite or products out of natural fiber composites, and that within the next 10 years we need to close the cost gap. We believe in a future where these market failure is overcome, that sustainability is priced into products and services. But meanwhile, we need to focus also on the price to have really big environmental impacts or release. So, and this is supported by the bottom-up pressure from the streets and the top-down pressure from the government, and our way to go is now to build up panel, or to bring sandwich panels from on an industrial level because on such a panel you could it's easier to have one product. You have where you could establish your concept for recycling, also with local partners, and for example the steel mills or the recycling companies here in Bremen, and to build different products out of these panels, like these boat on the top, small fishing boat, or the offshore with this offshore nacelle or a wind turbine. That's a very important step for us to have these environmental relief effects. And as you see, for structural components like these glass fiber informed plastics, where in Europe more than 1,000 tons are produced, if we could replace these conventional composites by natural fiber composites, and we also would have a big impact on CO2 and energy and so on. So the boat builders, I mean, these are numbers for the whole Europe. So the boat building industry or marine industry, due to the corona crisis, they are sold out, so there's a lot to do and a lot to replace, because until now there are only few boats and other parts which are really replaced, and yeah, so I think for all of us there is a lot to do. If there are questions, feel free. And yeah, thank you very much.
Okay, thank you very much for the reconnection and for still trying to give us the continuation of your presentation. Are there any questions here in the audience or from the people online? I see no hands raised. Do you think, I have one question, yes?
Given the closeness of the life cycle assessment for carbon and flax, and the fact that you've only used a single database, Marine Shift 360, which it's not clear where the data is coming from, it could be that a different package gives a different priority.
Yeah, that is true, but we are partners for this Marine Shift data, for this Marine Shift 360 tool, and we know also where the data is coming from. So I tried to for example, which is a big problem, for example, for the EcoInvent database, where you find a paper for flax, which takes, how do you say it, rotting? I don't know the English word, where you put the fiber in a water basin, or in France you just leave it on the field, you know what I mean? So they used a paper, or still, the EcoInvent database still relies on the paper where in India flax is produced and is put in a water basin by high temperatures, and of course this is not, if you compare it with the production way in France, you can't compare these numbers, and then of course you get quite high impacts if you use this EcoInvent database. This is a problem. But I like the idea to have one tool where everyone is, or where the whole industry could compare their results. Of course, this tool is not yet finished, and something like that needs to be such problems needs to be taken into account. Yeah. But as we know about these problems, we also were able to cope with these problems. So I changed the amounts according to the papers which are available for flax fiber from or also from our suppliers.
Do you think that your customers are also willing to pay more, just based on the fact that it's more sustainable, bio-based, or do you still see an important hurdle to take, that the price needs to be competitive with the now petroleum-based alternatives?
I think, of course, they are now our customers. Now they are willing to pay more because they pay more. It's like it is, and but we need also to work with those who are not willing to pay more. Of course, the costs who pay the future, how do you say, the future, our children in the future, they need to be priced in all the products, and then this is also not there's also, the difference is also not that high anymore. But I think for us it's now important to come from the small shipyard where we build everything by hand to a certain level where natural fiber are also produced on a semi-industrial level or on an industrial level, really have these environmental impacts and also to focus this price gap. Yeah.
Okay, thank you. Any other questions? I see no hands raised and no questions in the chat. So thank you very much for trying to reconnect, and thank you very much. Yes, please, go ahead.
Yeah, and for the moisture, because different people were talking about the moisture, or I have two questions actually. For the moisture, did you prepare or the ones who do tests, did they prepare the specimens? Were they did they finish or not? This is a question for the moisture, and the other question for the PLA question. Yeah, is there still someone who could answer that?
The question came. I don't think the question came fully through. So could you just repeat your question? We know it's about moisture, but we could not hear exactly your specific question.
Okay. Did the specimens did they have a top coat or a finish?
But I think we have different ones. So the work that Frederik has been explained doesn't have a top coat, and I think also the materials in our project, I don't know, John, your materials, they also don't have a top coat.
Interesting. Yeah.
No, so the materials are not top coated, so they are just processed as it were. So or compression molding or with other technology. Yes.
Yeah, I think when we worked on the Gualaz project, we did do tests to look at the effect of gel coats, top coats, and also paints, anti-fouling paints, and you can see very clearly the effect it has on slowing down water entry, but it doesn't stop it. So eventually the water does get in, but it allowed us to slow it down considerably.
Yeah, interesting. Yeah.
Yes.
Yeah, thank you very much.
But there is a school of thought that says a porous gel coat is a better bet because the water could get out again.
Okay. Yeah.
Okay. Does it answer your question, or do you still have other questions to ask?
No, that's it.
No, then I would say thank you very much. So as you already mentioned, you will also be present at the JAC in Paris next week. So for the people here, I also invited them if they're there to come and visit you. Also one of our partners, Chunhei, is present there, I think. Chunhei, you're also there. So also at the booth of IMT, you can also go and visit. There will also be a flyer of our project. So then I think we come to the end. We will try to share on our website also, if possible, the links, and then also we try to hope to put there the video of today. So if you want to have a look again of what have been presented, feel free to contact our website. We will also do a press release, so sharing some information on today's workshop. So then, last thing, thank you all for coming here. Thank you all for being online, and we hope to see you all back on one of our future events. We have seen there's still some challenges to solve, but let's go together for it. Thank you very much, everybody.